In the vast darkness of the outer solar system, far beyond the orbit of Saturn, there is a planet that behaves unlike any other world around the Sun. While most planets spin upright as they travel through space, one giant world appears to have fallen on its side. That planet is Uranus. Instead of rotating like Earth, Jupiter, or even its neighbor Neptune, Uranus spins at an astonishing angle of about 98 degrees. In other words, the planet is essentially rolling through space as it orbits the Sun. This strange orientation creates some of the most unusual seasons in the entire solar system. For decades at a time, one pole of Uranus points almost directly toward the Sun, while the other remains in complete darkness. Entire hemispheres experience continuous daylight or night for years. But how did this happen? Why is Uranus the only planet that rotates on its side? Scientists believe the answer may lie in the violent early history of the solar system, a time when young planets were still forming and massive collisions were common. Somewhere in the distant past, something may have struck Uranus with incredible force, knocking the entire planet sideways. Yet, the exact cause of this tilt remains one of the most intriguing mysteries in planetary science. In this documentary, we will explore why Uranus rotates sideways, what might have caused this dramatic tilt, and how this unusual orientation continues to shape the planet's seasons, atmosphere, and moons today. In order to understand why Uranus rotates sideways, we first need to understand how planets normally rotate and how the solar system formed billions of years ago. The strange tilt of Uranus is not just a curious detail about one distant planet. It is a clue that reveals the violent and chaotic history of the early solar system. About 4.6 billion years ago, the solar system began as a massive cloud of gas and dust known as the solar nebula. This cloud slowly collapsed under its own gravity, forming a rotating disk of material around the young sun. Within this disk, small particles of dust and ice began sticking together, forming larger and larger objects through a process called accretion. Over time, these growing bodies became planetesimals, small early building blocks of planets. As they collided and merged with one another, they gradually formed the planets we know today. During this early stage, the solar system was a far more chaotic place than it is now. Instead of the stable orbits we observe today, countless objects were moving through space, colliding with one another at enormous speeds. Planet formation was a violent process. Massive impacts between growing planetary bodies were common. In fact, many scientists believe that Earth's own moon formed when a Mars-sized object collided with the early Earth. Events like this were likely happening throughout the young solar system. Because of these repeated collisions, the planets we see today did not simply form quietly in their current states. Their shapes, rotations, and even their internal structures were influenced by the countless impacts that occurred during their formation. Most planets ended up rotating in roughly the same direction and orientation. If we observe the major planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and Neptune, we find that their rotational axes are tilted relative to their orbital planes, but only by moderate amounts. Earth, for example, is tilted by about 23.5 degrees. This tilt is responsible for the changing seasons we experience throughout the year. Mars has a tilt of about 25 degrees, producing seasonal changes similar to Earth's. Even giant planets like Jupiter and Saturn are only slightly tilted compared with the plane of their orbits. But Uranus is dramatically different. The rotational axis of Uranus is tilted by approximately 98 degrees. This means that the planet is essentially lying on its side, relative to the plane of its orbit around the Sun. If you could watch Uranus travel around the Sun from a distance, it would appear as though the planet is rolling along its orbit, rather than spinning upright like the other planets. This unusual orientation has profound consequences for the planet's behavior. Because Uranus is tilted so extremely, its poles experience long periods of sunlight and darkness unlike anything seen on Earth. Each pole spends about 42 years in continuous sunlight, followed by 42 years of darkness. This occurs because Uranus takes approximately 84 Earth years to complete one orbit around the Sun. During half of that orbit, one hemisphere faces the Sun almost directly, while the other remains pointed away from it. For decades at a time, large portions of the planet receive either constant daylight or constant night. These extreme seasons make Uranus one of the most unusual worlds in the solar system. The tilt also affects the planet's system of rings and moons. Unlike most planets whose rings orbit around their equators in a relatively flat plane, the rings of Uranus are oriented vertically relative to the Sun because they follow the planet's tilted equator. This creates an unusual appearance when viewed from Earth. Sometimes the rings appear wide and open, while at other times they seem to disappear almost completely when viewed edge-on. Uranus also possesses a complex system of moons that orbit around the tilted planet. Major moons such as Titania, Oberon, Umbriel, Ariel, and Miranda all follow orbits aligned with the planet's tilted equatorial plane. This means that the entire Uranian system, its rings and moons, shares the same sideways orientation. The question that naturally arises is how this happened. Why is Uranus so dramatically tilted when the other planets are not? For many years, scientists believed the most likely explanation was a massive collision. In this scenario, a large planetary body, possibly twice the size of Earth, struck Uranus during the early stages of the solar system. The impact would have delivered enough force to knock the planet onto its side, permanently altering its rotation. Such collisions were common during the early formation of planets, making this explanation plausible. Computer simulations have shown that a giant impact could indeed produce a tilt similar to what we observe today. However, there are still questions about whether a single impact could fully explain the current structure of the Uranian system. For example, if a massive collision occurred, we might expect Uranus to possess a large debris disk from which new moons formed. While Uranus does have moons, their arrangement and composition raise additional questions about whether a single collision could produce the system we observe today. Another challenge involves the internal structure of Uranus itself. Compared with other giant planets, Uranus emits surprisingly little internal heat. Most of the energy the planet radiates into space comes directly from sunlight, rather than from internal sources. Scientists are still trying to understand whether this unusual energy balance could be related to the event that caused Uranus to tilt. Some researchers have suggested that instead of one giant impact, Uranus may have experienced multiple smaller collisions. Several large impacts occurring over time could gradually tilt the planet without disrupting its internal structure as dramatically as a single massive collision might. Computer models exploring this possibility have produced results that match some of the characteristics of Uranus more closely. Another possibility involves gravitational interactions between young planets during the early solar system. As giant planets migrated through the protoplanetary disk, their gravitational forces may have disturbed one another's orbits and rotations. These interactions could potentially alter the tilt of a planet over time. Although the giant impact theory remains the most widely accepted explanation, the exact details of how Uranus acquired its extreme tilt are still being investigated. What makes Uranus particularly fascinating is that its unusual orientation affects nearly every aspect of the planet, from its atmosphere and magnetic field to its seasonal patterns and moon system. The sideways rotation of Uranus is not just a curiosity. It is a reminder that the solar system we see today was shaped by powerful and sometimes violent events during its early history. By studying Uranus, scientists gain valuable insights into the processes that formed planets, not only in our own solar system, but also around other stars. Because collisions between young planets are common during a planetary formation, understanding the story of Uranus may help astronomers interpret the unusual planetary systems being discovered across our galaxy. In many ways, Uranus stands as one of the most mysterious planets in the solar system. Its strange tilt hints at a dramatic past, one shaped by forces powerful enough to knock an entire planet sideways and leave it permanently rolling through space as it circles the Sun. After recognizing that Uranus rotates on its side, scientists began asking a deeper question. What kind of event could actually tilt an entire planet? Understanding this requires imagining the scale of the forces involved during the early solar system. Uranus is not a small object that can be easily knocked over. It is the third largest planet in the solar system, with a diameter of more than 50,000 kilometers and a mass about 14 times greater than Earth. To change the orientation of such a massive world requires an extraordinary amount of energy. For comparison, the energy released by the asteroid impact that likely caused the extinction of the dinosaurs on Earth was enormous. That asteroid was roughly 10 kilometers wide and released energy equivalent to billions of nuclear bombs. Yet an impact capable of tilting Uranus would have needed to be far larger. Scientists estimate that the object responsible for such a tilt might have been 1 to 3 times the mass of Earth. That means the collision would not have been a simple asteroid impact, but rather a planetary-scale crash between two massive bodies. During the earliest stages of the solar system, such events were possible because planets were still forming and moving through crowded regions filled with large planetary embryos. These embryos were leftover building blocks of planets that had not yet merged into stable worlds. Many of them were enormous, some nearly the size of Mars or Earth. When two objects this large collide, the result is catastrophic. Instead of simply bouncing off each other, the materials of both bodies partially melt, vaporize, and mix together. Huge quantities of debris can be thrown into space, sometimes forming rings or moons around the newly altered planet. This is exactly what scientists believe happened when Earth's moon formed. A massive impact between Earth and a Mars-sized body called Theia likely produced a disk of debris that eventually coalesced into the moon. A similar event may have occurred with Uranus. In the giant impact hypothesis, a large planetary embryo collided with Uranus during its early history. Instead of destroying the planet completely, the collision would have transferred angular momentum, effectively pushing the planet over onto its side. Computer simulations have been used to model this scenario. These simulations recreate collisions between large planetary bodies under different conditions, such as speed, angle, and mass. Some models show that a collision at the right angle could tilt Uranus by approximately 90 degrees, producing the sideways orientation we see today. However, scientists quickly realized that the situation might be more complicated. One of the first questions researchers asked was what should happen to the planet's moon system after such a collision. If a giant impact had occurred, we might expect Uranus to possess a massive debris disk that later formed its moons. Yet the moons of Uranus do not appear to be the direct products of a large debris disk like Earth's moon. Instead, the Uranian moons seem to have formed in a more orderly system, aligned with the planet's equator. This means that either the moons formed after the collision from a new disk of material, or that the collision occurred early enough for the moon system to reorganize itself afterward. Another challenge involves the internal structure of Uranus. Compared with its neighbor Neptune, Uranus appears to have a very different internal heat profile. While Neptune radiates significant heat from its interior, Uranus emits very little. This difference has puzzled astronomers for decades. If Uranus experienced a massive collision, that impact could have altered the internal layers of the planet, possibly mixing them in ways that trapped heat inside. Some models suggest that the collision could have created a layered internal structure where heat from the planet's core cannot easily escape. This might explain why Uranus appears unusually cold compared with Neptune. Another clue supporting the giant impact theory involves the magnetic field of Uranus. Most planets with magnetic fields have them aligned roughly with their rotational axes. Earth, for example, has a magnetic field generated by motions in its liquid outer core, and the magnetic poles are relatively close to the geographic poles. Uranus is very different. The planet's magnetic field is tilted by about 59 degrees relative to its rotational axis, and is also offset from the planet's center. This unusual magnetic geometry suggests that the internal structure of Uranus is quite complex. Some researchers believe that the giant impact that tilted Uranus could also have disturbed the internal layers responsible for generating the magnetic field. The result may be a magnetic dynamo operating in an unusual region within the planet, rather than near its core. While the giant impact hypothesis explains many aspects of Uranus, scientists continue to investigate alternative possibilities. One alternative idea suggests that Uranus may not have been knocked over by a single collision, but instead by a series of smaller impacts. In this scenario, multiple large objects struck Uranus over millions of years. Each collision would slightly alter the planet's tilt. Gradually, these repeated impacts could have pushed Uranus farther and farther over until it reached its current orientation. This idea has certain advantages. Multiple smaller impacts might produce a smoother change in tilt, while leaving the planet's internal structure less dramatically disturbed than a single massive collision would. Simulations exploring this idea have shown that several collisions with objects roughly 1/10 to 1/5 the mass of Earth could gradually tilt a planet over time. Another possibility involves gravitational interactions with nearby planets. During the early solar system, the giant planets Jupiter, Saturn, Uranus, and Neptune may not have formed exactly where they are today. Some models of solar system evolution suggest that the giant planets migrated through the protoplanetary disk before settling into their current positions. During this migration, strong gravitational interactions between planets could potentially alter their rotational orientations. However, most models indicate that gravitational effects alone are unlikely to produce the extreme 98-degree tilt observed on Uranus. This makes the impact explanation still the most convincing scenario. Even today, scientists continue to refine their understanding of how Uranus acquired its sideways rotation. Observations of exoplanets, planets orbiting other stars, have shown that unusual tilts and orbital configurations are surprisingly common in the universe. Some exoplanets appear to orbit their stars at extreme angles, and some may even rotate in unusual orientations similar to Uranus. This suggests that dramatic planetary events may be a normal part of planet formation. The story of Uranus, therefore, provides a valuable example of how chaotic and unpredictable the early stages of planetary systems can be. What we observe today, the stable arrangement of planets orbiting quietly around the Sun, represents the end result of billions of years of evolution following a much more violent beginning. Uranus still carries the mark of that ancient chaos. Its sideways rotation serves as a cosmic fossil of a collision or series of events that occurred billions of years ago when the solar system was still forming. And while scientists continue searching for the exact explanation, every new observation and simulation brings us a little closer to understanding how one of the strangest planets in the solar system came to roll through space on its side. Understanding the sideways rotation of Uranus also requires looking closely at the planet itself, its structure, composition, atmosphere, and the unusual environment created by its extreme tilt. Unlike the rocky worlds of the inner solar system, Uranus belongs to a class of planets known as ice giants, a category that includes only two members, Uranus and Neptune. Although the name might suggest that these planets are made entirely of ice, the reality is more complex. Ice giants contain large amounts of substances such as water, methane, and ammonia that were frozen in the cold outer regions of the early solar system. Deep inside the planet, these materials exist not as solid ice, but as extremely hot, dense fluids under enormous pressure. The outermost layer of Uranus is its atmosphere, composed primarily of hydrogen and helium, with smaller amounts of methane. It is the methane that gives Uranus its distinctive blue-green color. Methane absorbs red wavelengths of sunlight, while reflecting blue and green light back into space, creating the soft turquoise appearance seen in telescope images. Beneath the atmosphere lies a thick mantle, composed largely of water, ammonia, and methane ices. Under the extreme pressure and temperature conditions inside the planet, these materials form exotic states of matter that do not exist naturally on Earth. At the center of Uranus is a rocky core thought to be only slightly larger than Earth. Despite its enormous size, Uranus is actually the coldest planetary atmosphere in the solar system. Temperatures in its upper atmosphere can drop to around minus 224 degrees Celsius. This is surprising because Uranus receives only slightly less sunlight than Neptune, yet Neptune is significantly warmer internally. Scientists believe the explanation may again be connected to the event that tilted Uranus on its side. If Uranus experienced a massive collision early in its history, that impact might have altered the planet's internal layers. Some researchers propose that the collision created a stratified structure in which different layers of material do not mix easily. If heat from the core cannot move efficiently through these layers, it may become trapped inside the planet. This could explain why Uranus radiates very little internal heat compared with Neptune. Another remarkable feature of Uranus is its atmospheric behavior. For many years, astronomers believed that Uranus was a relatively calm planet, with few storms or cloud formations. Early images from telescopes showed a smooth, nearly featureless atmosphere. However, later observations revealed that Uranus can produce powerful storms and complex cloud systems. Large, bright clouds occasionally appear in the atmosphere, some of which may be massive storm systems driven by seasonal changes. These storms can grow to enormous sizes and move rapidly through the planet's atmosphere. The sideways rotation of Uranus has a dramatic influence on these atmospheric processes. Because the planet is tilted by 98 degrees, its seasons are unlike those of any other planet. Each pole spends decades pointed almost directly at the sun. During this time, that hemisphere experiences continuous daylight, while the opposite hemisphere remains in darkness. These long periods of extreme illumination and darkness cause enormous temperature differences between different regions of the planet. As Uranus slowly moves along its 84-year orbit around the Sun, sunlight gradually shifts from one hemisphere to the other. The transition between these phases can produce changes in atmospheric circulation and storm activity. Astronomers have observed increased storm activity near the time of Uranus's equinox, when the sun shines directly over the planet's equator. At this point, sunlight begins illuminating both hemispheres more evenly. These seasonal shifts may drive strong winds and cloud formations in the upper atmosphere. Another intriguing feature of Uranus is its ring system. Although not as spectacular as Saturn's rings, Uranus does possess a collection of narrow rings composed of dark particles of ice and rock. These rings orbit around the planet's equator, meaning they share the same extreme tilt as Uranus itself. From Earth, this creates a fascinating viewing effect. At certain times in Uranus's orbit, the rings appear wide and clearly visible. At other times, when the rings are edge-on to Earth, they become extremely difficult to detect and may even disappear from view. The rings of Uranus were discovered in 1977, when astronomers observed the planet passing in front of a distant star. As the planet moved across the star's light, the brightness briefly dimmed several times before and after the main eclipse. These dips revealed the presence of rings surrounding the planet. In addition to its rings, Uranus has a large family of moons. The 5 largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, orbit the planet in the same tilted plane as the rings. These moons are believed to have formed from material orbiting around Uranus early in its history. Some scientists think that the sideways tilt of Uranus may have influenced the formation and evolution of these moons. If a giant impact occurred, it might have created a temporary disk of debris from which the moons later formed. One of the most unusual moons in this system is Miranda. Miranda's surface is filled with enormous cliffs, deep canyons, and strange patchwork regions that appear to have been violently disrupted in the past. One of its most famous features is Verona Rupus, a cliff estimated to be nearly 20 kilometers high, making it one of the tallest known cliffs in the solar system. Scientists believe Miranda's strange landscape may have been shaped by powerful tidal forces from Uranus combined with geological activity in the moon's past. The entire Uranian system, its rings and moons, appears to share the same tilted orientation as the planet itself. This suggests that whatever event caused Uranus to rotate sideways likely occurred very early in the planet's history, before the current moon system fully formed. Studying Uranus is challenging because the planet is extremely distant from Earth. Uranus orbits the Sun at an average distance of about 2.9 billion kilometers, nearly 20 times farther from the Sun than Earth. Because of this enormous distance, the planet appears very small and faint, even in powerful telescopes. So far, only one spacecraft has visited Uranus. In 1986, NASA's Voyager 2 spacecraft flew past the planet during its journey through the outer solar system. This historic flyby provided the first close-up images of Uranus and its moons. Voyager 2 revealed the planet's ring system, measured its magnetic field, and discovered several new moons. However, the spacecraft had only a brief opportunity to observe the planet before continuing its mission toward Neptune. As a result, many aspects of Uranus remain poorly understood. Today, scientists are increasingly interested in sending new missions to study Uranus in greater detail. Future spacecraft could examine the planet's atmosphere, interior, magnetic field, and moon system more closely. Such missions may help answer some of the remaining questions about the planet's unusual tilt. By studying Uranus, scientists hope to learn not only about this mysterious world, but also about how planetary systems evolve. The strange sideways rotation of Uranus reminds us that the solar system is not a static or perfectly orderly place. Instead, it is the result of billions of years of collisions, migrations, and gravitational interactions. Uranus stands as a quiet witness to that turbulent past, a giant world that still carries the mark of an ancient cosmic event, powerful enough to tip an entire planet onto its side. The extreme tilt of Uranus does more than simply change the way the planet rotates. It completely transforms how sunlight reaches the planet and creates one of the most unusual seasonal cycles anywhere in the solar system. To understand how dramatic these seasons are, we need to imagine what Uranus experiences during its long journey around the Sun. Uranus takes about 84 Earth years to complete one full orbit. This means that a single year on Uranus lasts longer than an entire human lifetime. Because the planet is tilted by about 98 degrees, its poles point almost directly toward the Sun during certain parts of this orbit. For roughly 1/4 of its orbit, the North Pole faces the Sun almost continuously. During this time, the northern hemisphere experiences constant daylight that lasts more than 20 Earth years. The sun never sets for decades. Meanwhile, the southern hemisphere remains in complete darkness. Then, as Uranus continues its orbit, the situation gradually reverses. The sun begins illuminating the equatorial regions, producing a period somewhat similar to the equinoxes on Earth. Eventually, the South Pole turns toward the sun, and the southern hemisphere enters its own long period of continuous daylight. Each hemisphere therefore experiences about 42 years of sunlight, followed by 42 years of darkness. These extreme seasonal cycles are unlike anything on Earth or on most other planets. On Earth, the tilt of our planet is moderate, and the sun rises and sets every day in most places. Even near the poles, the periods of continuous daylight or darkness last only a few months. On Uranus, entire generations of potential observers could live through decades of unbroken daylight or night. Scientists originally expected these extreme seasons to produce enormous temperature differences across the planet. If one hemisphere receives sunlight for decades, while the other remains in darkness, it seems logical that one side would become much warmer than the other. However, observations have revealed something surprising. Uranus appears to have a relatively uniform temperature distribution across much of its atmosphere. The differences between sunlit and dark regions are smaller than expected. This suggests that the planet's atmosphere is very efficient at redistributing heat. Strong winds and atmospheric circulation likely move energy around the planet, smoothing out temperature differences that would otherwise become extreme. Even so, seasonal changes do influence the atmosphere. When Uranus approached its equinox in 2007, astronomers observed a sudden increase in atmospheric activity. Large, bright clouds appeared in the atmosphere, and powerful storms began forming at mid-latitudes. These storms were detected using powerful telescopes, such as the Hubble Space Telescope, and large ground-based observatories. Some of the clouds observed were thousands of kilometers across. These findings suggested that the long seasonal cycles of Uranus may drive dramatic changes in atmospheric circulation over time. Another unusual aspect of Uranus involves the orientation of its magnetic field. On most planets with magnetic fields, the magnetic axis is roughly aligned with the planet's rotational axis. Earth's magnetic poles, for example, are relatively close to the geographic poles. Uranus again behaves very differently. The planet's magnetic field is tilted by about 59 degrees relative to its rotational axis, and the center of the magnetic field is offset significantly from the center of the planet. This means that as Uranus rotates, its magnetic field swings through space in an unusual, wobbling motion. The result is a highly complex and dynamic magnetosphere, the region of space influenced by the planet's magnetic field. Charged particles from the solar wind interact with this magnetosphere, creating strange patterns of radiation around the planet. Scientists believe this unusual magnetic configuration may be connected to the internal structure of Uranus. Unlike Earth, where the magnetic field is generated by a molten iron core, the magnetic fields of Uranus and Neptune are thought to originate in layers of electrically conducting fluids composed of water, ammonia, and methane. Because the internal structure of Uranus may have been disrupted by the event that tilted the planet, The region generating the magnetic field could be located in an unusual position inside the planet. This might explain why the magnetic field appears offset and tilted. Another fascinating feature related to Uranus's sideways orientation is how its rings and moons interact with sunlight. Because the entire system is tilted, the rings sometimes appear nearly vertical relative to the Sun. At certain points in Uranus's orbit, sunlight shines directly onto the rings, making them more visible. At other times, the rings are illuminated from the side, making them extremely difficult to detect. Astronomers occasionally witness ring plane crossings, events in which the rings appear almost invisible from Earth because we are viewing them exactly edge-on. During these times, even powerful telescopes may struggle to detect the rings. The moons of Uranus experience similar seasonal extremes. Because they orbit in the same tilted plane as the planet's equator, the moons also experience long periods of sunlight and darkness as they circle Uranus, for decades at a time. Certain regions of these moons may remain in continuous daylight, while others remain in darkness. This unusual pattern may influence the temperatures and surface processes on these distant worlds. Despite all these fascinating characteristics, Uranus remains one of the least explored planets in the solar system. Since the brief flyby of Voyager 2 in 1986, no spacecraft has returned to study the planet up close. Most of what scientists know today comes from observations made by telescopes on Earth and in orbit around our planet. However, interest in Uranus has grown significantly in recent years. Planetary scientists consider Uranus to be a high-priority target for future exploration missions. A dedicated spacecraft placed in orbit around the planet could study its atmosphere, magnetic field, interior, rings and moons in far greater detail. Such a mission might help answer long-standing questions about how Uranus formed and how it acquired its unusual tilt. It could also provide valuable information about ice giant planets, a type of world that appears to be very common in other planetary systems. Many of the exoplanets discovered around distant stars are similar in size to Uranus and Neptune. Understanding these planets in our own solar system could therefore help scientists interpret the growing number of planetary systems discovered across the galaxy. The sideways rotation of Uranus remains one of the most striking features of the solar system. It transforms the planet's seasons, influences its atmosphere, shapes its ring system, and creates a magnetic environment unlike any other world. Whether the result of a giant collision, multiple impacts, or a more complex sequence of events, this unusual tilt serves as a reminder that the formation of planets is rarely simple or orderly. Instead, it is a process shaped by powerful forces capable of altering entire worlds, leaving behind planets like Uranus that continue to spin sideways through space billions of years after the events that changed them forever. When scientists study the strange sideways rotation of Uranus, they are not just trying to explain one unusual planet. They are also trying to understand how planetary systems form and evolve throughout the universe. The tilt of Uranus is a reminder that the early solar system was not a calm and orderly place. Instead, it was a chaotic environment where giant worlds were still growing, colliding, and reshaping one another. During the first hundreds of millions of years after the Sun formed, the solar system contained many more large bodies than it does today. These objects included planetary embryos, large masses of rock and ice that had begun forming into planets but had not yet reached their final sizes. These embryos moved through the young solar system in unstable orbits. Because the giant planets were still forming and migrating through the protoplanetary disk, gravitational interactions between planets and embryos frequently altered their paths. Some objects were thrown outward toward the distant regions of the solar system, while others were sent inward toward the sun. In this chaotic environment, collisions between massive objects were almost inevitable. The impact that may have tilted Uranus likely occurred during this early stage. If a planetary embryo collided with Uranus while the planet was still forming, the energy released would have been immense. Such an event could easily alter the rotation of the planet and reshape its internal structure. Computer simulations have helped scientists explore how such collisions might occur. These simulations show that the outcome of a planetary impact depends strongly on the angle and speed of the collision. A direct head-on impact might shatter a planet or merge the two bodies together. But a glancing collision, where the impactor strikes at an angle, can transfer enormous angular momentum without completely destroying the planet. In the case of Uranus, many models suggest that a glancing collision may be the most likely explanation. In this scenario, the impacting body would strike Uranus at an angle rather than directly. Instead of destroying the planet, the collision would push it sideways while leaving much of its structure intact. Material from both bodies might have been thrown into orbit, forming a temporary disk of debris around the planet. Over time, this debris could have combined to form some of the moons that orbit Uranus today. But the effects of such an impact would not stop with the planet's rotation. The collision could also affect the internal layers of Uranus. Most giant planets have internal structures that allow heat from their cores to escape gradually into space. This internal heat helps drive atmospheric motion and contributes to the overall energy balance of the planet. Neptune, for example, radiates about twice as much energy as it receives from the Sun. Uranus is very different. The planet emits only slightly more energy than it receives from sunlight. In other words, Uranus appears to have very little internal heat escaping from its interior. This unusual property has puzzled scientists for decades. One possible explanation is that the event that tilted Uranus also disrupted the internal layers of the planet in a way that trapped heat deep inside. Some models suggest that the impact could have caused the interior to become stratified, meaning that layers of material with different compositions became separated. If these layers do not mix easily, heat from the core may remain trapped instead of rising toward the surface. This would help explain why Uranus appears colder than Neptune, despite having a similar size and composition. The sideways tilt of Uranus may therefore be connected not only to the planet's rotation, but also to its internal structure and thermal history. Another intriguing question involves the timing of the collision. Did the impact occur before the Uranian moon system formed, or did it happen afterward? If the collision occurred early, the moons could have formed from the debris disk created by the impact. This would mean that the moons and rings naturally share the same tilted orientation as the planet. However, if the collision occurred after the moons had already formed, the entire moon system would need to have been tilted along with the planet. This possibility is less likely because it would require enormous gravitational forces acting on the moons. Most scientists therefore believe that the tilt occurred relatively early in the history of Uranus, before the current moon system fully developed. Another important factor in understanding Uranus involves the migration of giant planets in the early solar system. According to one widely accepted model known as the NICE model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not always occupy their present orbits. Instead, they may have formed closer together and later migrated outward as they interacted with a disk of smaller icy bodies. During this migration, gravitational interactions between the planets could have triggered periods of instability. These events may have caused close encounters between planets and planetary embryos, increasing the likelihood of giant impacts. Such chaotic interactions could easily lead to collisions capable of altering the rotation of a planet. If Uranus experienced such a collision during this period of instability, it might explain why its tilt is so extreme compared with the other giant planets. Interestingly, Uranus is not the only planet in the solar system with an unusual rotational orientation. Venus also rotates in a strange way. Unlike most planets, Venus spins in the opposite direction from its orbit around the Sun. This retrograde rotation means that the Sun would appear to rise in the west and set in the east if one could stand on the surface of Venus. Some scientists believe that Venus may also have experienced major impacts during its formation that altered its rotation. Although the details are different, both Venus and Uranus demonstrate how planetary collisions can dramatically influence the final properties of a world. Studying Uranus therefore helps scientists understand how common such events may be during planet formation. Observations of exoplanets have revealed that planetary systems around other stars often contain worlds in unusual orbits and orientations. Some exoplanets appear to orbit their stars at extreme angles relative to the star's rotation. Others may have chaotic orbital histories shaped by gravitational interactions and collisions. These discoveries suggest that the formation of planetary systems can be far more violent and unpredictable than previously imagined. In this broader context, Uranus may not be as unusual as it first appears. Instead, it may represent a natural outcome of the chaotic processes that shape planetary systems. The sideways rotation of Uranus stands as evidence of a dramatic event that occurred billions of years ago, a cosmic collision powerful enough to tip an entire planet onto its side. Although the details of that event remain uncertain, the clues preserved in the planet's tilt, internal structure, and moon system continue to guide scientists as they search for answers. By studying Uranus, astronomers are not only solving the mystery of one planet, but also uncovering the story of how planets everywhere are born, evolve, and sometimes collide in the vast and dynamic environments of planetary systems throughout the universe. The sideways rotation of Uranus also has profound consequences for the way the planet interacts with sunlight and energy from the Sun. Because the planet's axis is tilted by about 98 degrees, its poles and equator experience sunlight in a completely different way compared with most other planets in the solar system. To imagine this more clearly, picture the orbit of Uranus around the Sun. Most planets spin like tops as they travel along their orbits, with their poles pointing roughly upward relative to the orbital plane. Uranus, however, is almost lying on its side. Its rotational axis is nearly parallel to the plane of its orbit. This means that during large portions of its 84-year orbit, one pole of Uranus is pointed almost directly at the Sun. When this happens, that pole experiences continuous daylight for decades. The Sun circles slowly around the sky without ever setting. Meanwhile, the opposite pole remains in complete darkness for the same long period. Each hemisphere therefore experiences about 42 years of sunlight, followed by 42 years of darkness. This pattern produces seasonal cycles unlike anything seen on Earth. On our planet, the tilt of about 23 degrees causes relatively mild seasonal changes. The Sun's position in the sky shifts gradually during the year, but every place on Earth still experiences daily cycles of sunrise and sunset. On Uranus, entire hemispheres may go decades without a single sunrise or sunset. One might expect these extreme conditions to create enormous differences in temperature between the sunlit and dark sides of the planet. However, observations have shown that Uranus's atmosphere does not display temperature contrasts as dramatic as expected. The reason appears to be the efficiency of the planet's atmospheric circulation. Strong winds high in the atmosphere help redistribute heat across the planet. Even when one hemisphere receives more sunlight, energy can be transported toward the darker regions through atmospheric motion. Although Uranus appears relatively calm compared with other giant planets, its atmosphere can still produce powerful winds. Some wind speeds on Uranus reach more than 900 kilometers per hour. These winds move clouds and atmospheric gases around the planet, helping balance temperatures between different regions. Seasonal changes still influence the planet's weather patterns. When Uranus approaches the point in its orbit where the Sun shines over its equator, an event called an equinox, the distribution of sunlight becomes more balanced between the northern and southern hemispheres. During these times, astronomers have observed an increase in atmospheric activity. Large, bright clouds appear in the upper atmosphere, and powerful storms develop at certain latitudes. These storms may form as temperature gradients shift and atmospheric circulation reorganizes itself. Such events provide scientists with rare opportunities to study the dynamics of the planet's atmosphere. The long seasons of Uranus also affect its moons. Because the moons orbit around the planet's tilted equator, they experience similar patterns of illumination. Certain regions of the moons may remain in sunlight for decades, while others remain in darkness. This could influence the temperature cycles and surface processes occurring on these distant icy worlds. Another fascinating consequence of Uranus's tilt involves its ring system. Uranus has a collection of narrow rings composed of dark particles made of ice and rock. These rings orbit around the planet's equatorial plane, meaning they share the same sideways orientation as the planet itself. As Uranus moves along its orbit, the angle at which sunlight strikes the rings changes dramatically. At certain points in the planet's orbit, The rings are illuminated from above, making them easier to observe. At other times, sunlight strikes the rings edge on, making them appear extremely thin or even invisible from Earth. Astronomers occasionally observe ring plane crossings when Earth passes through the same plane as the rings. During these events, the rings become almost impossible to see because their thin edges reflect very little sunlight toward our telescopes. These moments provide scientists with unique opportunities to study faint moons and small particles within the ring system that might otherwise be hidden by the brighter ring structures. Perhaps the most unusual feature influenced by Uranus's tilt is its magnetic field. Most planets generate magnetic fields through motions of electrically conducting fluids inside their interiors. On Earth, the magnetic field is produced by the movement of molten iron within the outer core. For many planets, the magnetic field is roughly aligned with the rotational axis. Uranus, again, behaves very differently. The planet's magnetic field is tilted about 59 degrees relative to its rotational axis and is significantly offset from the center of the planet. This creates a magnetosphere with a highly irregular shape. As Uranus rotates, its magnetic field sweeps through space in a complex motion, producing unusual patterns in the surrounding magnetic environment. Charged particles from the solar wind interact with this magnetosphere, creating dynamic radiation regions around the planet. Scientists believe the strange geometry of Uranus's magnetic field may be connected to the structure of its interior. Instead of forming deep in a central metallic core, the magnetic field may originate within a layer of electrically conducting fluids composed of water, ammonia, and methane under extreme pressure. If the internal structure of the planet was disrupted by the event that tilted Uranus, this could explain why the magnetic field appears misaligned and offset. The interaction between Uranus's magnetic field and its atmosphere also produces unusual auroras. On Earth, auroras occur when charged particles from the solar wind interact with the magnetic field near the poles, producing glowing curtains of light in the upper atmosphere. Because Uranus's magnetic field is tilted and offset, its auroras behave differently. They may appear in unexpected locations and shift in complex patterns as the planet rotates. Observations of these auroras help scientists study the structure of the magnetosphere and the way energy flows through the planet's magnetic environment. Despite the progress scientists have made in understanding Uranus, many questions remain unanswered. Much of what we know about the planet comes from the brief flyby of the Voyager 2 spacecraft in 1986 and from observations made by powerful telescopes. Voyager 2 provided humanity's only close-up look at Uranus so far, revealing its rings, moons, magnetic field, and basic atmospheric properties. However, the spacecraft passed by the planet quickly, giving scientists only a short time to collect data. As a result, many aspects of Uranus remain mysterious. Planetary scientists have proposed new missions to explore Uranus in greater detail. A future spacecraft placed into orbit around the planet could study its atmosphere, magnetic field, interior structure, and moon system for many years. Such a mission would help answer questions about how the planet formed, how its unusual tilt developed, and how its internal processes work. Studying Uranus is also important for understanding planets beyond our solar system. Many of the exoplanets discovered around other stars appear to be similar in size to Uranus and Neptune. These ice giant-type planets may be among the most common types of planets in the galaxy. By learning more about Uranus, scientists can better understand how these distant worlds might behave. The sideways rotation of Uranus therefore offers more than just an interesting curiosity. It provides valuable insight into the dynamic processes that shape planets and planetary systems. The unusual tilt of this distant world continues to challenge scientists and inspire new questions about the violent events that may have shaped the early solar system billions of years ago. To fully understand why Uranus rotates sideways, scientists also study the broader history of the outer solar system. Uranus did not form in isolation. Instead, it developed within a region populated by other giant planets, icy bodies, and countless smaller objects left over from the early stages of planetary formation. In the distant regions beyond the orbit of Jupiter, the early solar system contained enormous amounts of ice-rich material. Temperatures in these outer zones were cold enough for water, methane, and ammonia to freeze into solid form. These materials accumulated into growing planetary embryos, eventually forming the ice giants Uranus and Neptune. During this period, the giant planets were still interacting gravitationally with one another. Their orbits were not yet fully stable. Many models suggest that the outer solar system experienced a period of dramatic reorganization known as planetary migration. In this process, the giant planets gradually shifted their positions within the solar system. One widely accepted theory explaining this evolution is called the Nice model, named after the city in France where it was developed. According to this model, Jupiter, Saturn, Uranus, and Neptune originally formed closer together than they are today. Beyond them lay a massive disk of icy objects, similar to those now found in the Kuiper Belt. As the giant planets interacted gravitationally with this disk, they began exchanging angular momentum with the smaller bodies. Over time, this caused some planets to move outward, while others shifted slightly inward. These movements destabilized the orbits of many objects in the outer solar system. Large numbers of icy bodies were scattered into new regions, some being ejected completely from the solar system, while others were sent inward toward the Sun. This chaotic phase may have triggered a period known as the Late Heavy Bombardment, during which many planets and moons experienced intense impact activity. If Uranus experienced its tilting collision during this time, it would have occurred in an environment already filled with large moving objects capable of producing such an impact. One possibility is that Uranus collided with a large planetary embryo that had been scattered into its orbit by gravitational interactions with the other giant planets. Another possibility is that Uranus experienced multiple encounters with large objects that gradually altered its rotation. Computer simulations of planetary migration have shown that these interactions can produce highly unusual outcomes. Planets may be pushed into new orbits, captured into resonances with other planets, or even ejected entirely from the solar system. The sideways tilt of Uranus may therefore represent a fossil record of this chaotic era. Another clue about the planet's unusual history comes from the way Uranus rotates compared with its orbit. Most planets in the solar system rotate in the same direction in which they orbit the Sun. Uranus technically follows this pattern, but because its axis is tilted so far, its rotation appears very unusual. From certain perspectives, Uranus seems almost to rotate backward. In addition, Uranus rotates relatively quickly. A single day on Uranus lasts about 17 hours, meaning the planet spins rapidly despite its sideways orientation. The fact that Uranus still rotates quickly suggests that whatever event tilted the planet did not slow its spin dramatically. Instead, it likely altered the direction of the rotational axis while preserving much of the original rotational energy. This observation provides additional constraints for scientists modeling the possible collision scenarios. The impact would have needed to deliver enough angular momentum to tilt the planet while leaving the rotation speed relatively intact. Another intriguing aspect of Uranus involves its moon system. The planet currently has 27 known moons, most of which are relatively small compared with the large moons of Jupiter or Saturn. The 5 largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, form the primary inner moon system. All of these moons orbit in the same tilted plane as Uranus's equator. This alignment suggests that the moon system formed after the planet acquired its tilt. If the moons had formed before the tilting event, the impact would have needed to reorient their orbits as well, which would require enormous gravitational disturbances. Instead, many scientists believe that the moons formed from material orbiting Uranus after the planet had already been tilted. Some models propose that the collision that tipped Uranus may have created a debris disk composed of icy fragments from the impactor and the outer layers of Uranus. Over time, this debris could have gathered together to form the moons we observe today. The surfaces of the Uranian moons provide additional clues about the history of the system. Images captured by the Voyager 2 spacecraft revealed landscapes filled with craters, ridges, valleys, and mysterious geological features. Some moons appear heavily cratered, suggesting ancient surfaces that have remained unchanged for billions of years. Others show signs of past geological activity. Miranda, for example, displays enormous cliffs and unusual patchwork terrain that suggest parts of its surface may have been reshaped or reassembled by powerful internal forces. These features may be related to gravitational interactions between the moons and Uranus itself. Tidal forces generated by the planet's gravity can create internal heating inside moons, potentially driving geological activity. Although Uranus receives relatively little sunlight due to its distance from the Sun, tidal forces may have played a role in shaping the surfaces of some of its moons. The tilted orientation of the Uranian system also influences how sunlight reaches the moons. As Uranus travels through its 84-year orbit, sunlight gradually shifts from one hemisphere of the planet to the other. This means that the moons experience extremely long seasonal cycles similar to those of the planet itself. Regions of these moons may remain illuminated or dark for decades at a time. These unusual lighting conditions may influence the distribution of surface ice and the temperature cycles experienced by the moons. Despite these fascinating characteristics, Uranus remains one of the least explored planets in the solar system. Only a single spacecraft has visited the planet, and that encounter lasted only a short time. As a result, many aspects of the Uranian system remain poorly understood. Scientists continue to analyze data from Voyager 2 and observations from modern telescopes to uncover more details about the planet and its moons. Future exploration missions could dramatically expand our knowledge of Uranus. A spacecraft placed into orbit around the planet could study its atmosphere, rings, magnetic field, and moon system over many years. Such a mission might also measure the planet's gravitational field and internal structure, providing new clues about the events that shaped its unusual rotation. Understanding Uranus is not only important for studying our own solar system. Ice giants like Uranus appear to be extremely common among the exoplanets discovered around other stars. Many of these distant worlds may have similar sizes, compositions, and possibly even unusual tilts. By studying Uranus in detail, scientists can develop models that help explain how these planets form and evolve. The sideways rotation of Uranus remains one of the most striking examples of how dramatic events in the early solar system can leave lasting marks on planets billions of years later. The planet continues to spin on its side as it travels through space, carrying with it the silent evidence of a violent event that occurred long before the Earth itself had fully formed. And as scientists continue exploring the mysteries of this distant world, Uranus offers a powerful reminder that even the largest planets can bear the scars of ancient cosmic collisions. Even after decades of research, Uranus continues to remain one of the most mysterious planets in our solar system. While spacecraft have visited Jupiter, Saturn, and even Neptune, Uranus has only been explored once, during the brief flyby of the spacecraft Voyager 2 in 1986. That short encounter provided the first close look at the planet, but it also revealed how little we truly know about this distant world. When Voyager 2 approached Uranus, scientists expected to see a dynamic atmosphere, similar to the turbulent storms observed on planets like Jupiter and Saturn. Instead, the spacecraft observed a pale blue sphere that appeared almost featureless. For a time, Uranus became known as the most visually calm planet in the solar system. But this calm appearance turned out to be somewhat misleading. Years after the Voyager mission, astronomers using powerful telescopes began to notice subtle changes in Uranus's atmosphere. Bright cloud structures appeared at certain latitudes, and storms sometimes developed that were large enough to be seen from Earth with advanced telescopes. These discoveries suggested that Uranus is far more dynamic than the Voyager images first indicated. Part of the reason Voyager saw such a quiet atmosphere may be related to the planet's unusual seasons. When the spacecraft flew past Uranus, the sun was shining almost directly over one of the planet's poles. Because of the extreme tilt of the planet, much of the atmosphere may have been experiencing relatively stable conditions during that period. As the planet moved farther along its orbit around the sun, new atmospheric patterns began to emerge. These seasonal changes may play an important role in shaping the weather systems of Uranus. Over decades, sunlight gradually shifts from one hemisphere to the other. As this happens, temperature gradients across the planet change, which may drive new wind patterns and storm activity. Despite the planet's calm appearance, Uranus still hosts powerful winds. Observations suggest that some winds in its atmosphere can exceed 900 kilometers per hour. These winds move enormous cloud structures across the planet's upper atmosphere, redistributing heat and energy across different regions. Another fascinating feature discovered by Voyager 2 was the planet's ring system. Although far less spectacular than the bright rings of Saturn, Uranus possesses a set of narrow rings composed of dark particles. These rings are made primarily of icy fragments mixed with darker materials that absorb sunlight rather than reflecting it brightly. The rings are relatively thin and sharply defined. Some are only a few kilometers wide but extend tens of thousands of kilometers around the planet. Because Uranus rotates sideways, its rings share the same tilted orientation. This means that during different parts of the planet's long orbit, the rings can appear dramatically different when viewed from Earth. At certain times, astronomers see the rings almost from above, making them easier to observe. At other times, Earth lies nearly in the same plane as the rings, causing them to appear edge-on and extremely faint. These events, known as ring plane crossings, allow scientists to study the structure of the rings in greater detail. In addition to its rings, Uranus also possesses a fascinating collection of moons. The planet currently has 27 known moons, each with unique characteristics and geological histories. Many of these moons were discovered during the Voyager 2 mission, which revealed several previously unknown worlds orbiting the planet. The 5 largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, form the primary inner system. Among these moons, Miranda stands out as one of the most unusual objects in the solar system. Its surface appears almost chaotic, with enormous cliffs, deep valleys, and strange patchwork terrain. One of its most dramatic features, known as Verona Rupes, is an enormous cliff estimated to be around 20 kilometers high, making it one of the tallest cliffs known anywhere in the solar system. Scientists believe Miranda's strange landscape may have been shaped by a combination of internal geological activity and powerful tidal forces generated by Uranus. Other moons in the system display different geological histories. Some appear heavily cratered, suggesting ancient surfaces that have changed little over billions of years. Others show evidence of tectonic activity or resurfacing events that altered their landscapes. The moons of Uranus orbit in the same tilted plane as the planet's equator. This alignment supports the idea that the moon system formed after Uranus had already been tilted. One possibility is that a giant collision produced a disk of debris around the planet. Over time, this debris could have gradually gathered together to form the moons we see today. Another intriguing mystery surrounding Uranus involves its internal structure. Unlike Jupiter and Saturn, which emit large amounts of internal heat, Uranus radiates very little energy compared with the sunlight it receives. In fact, Uranus appears to have the coldest planetary atmosphere in the solar system. Scientists are still trying to understand why this is the case. One possibility is that the event that tilted Uranus also disrupted the internal layers of the planet. If the interior became stratified into layers that do not mix easily, heat from the core might remain trapped deep inside the planet, rather than escaping into the atmosphere. This could explain why Uranus appears colder than Neptune, even though both planets have similar sizes and compositions. Another remarkable property of Uranus is its magnetic field. Unlike Earth's magnetic field, which is roughly aligned with the planet's rotational axis, Uranus's magnetic field is tilted dramatically and offset from the planet's center. This unusual geometry creates a magnetosphere with a complex and constantly shifting structure. As Uranus rotates, its magnetic field sweeps through space in a motion that produces changing interactions with the solar wind. These interactions generate unusual auroras and radiation patterns around the planet. Understanding this magnetic field may provide important clues about the internal composition of Uranus and the processes occurring deep within the planet. Despite all the progress scientists have made, Uranus remains one of the least understood major planets. Because the planet is so distant, nearly 3 billion kilometers from the Sun, it is difficult to observe in detail. Even powerful telescopes can reveal only limited information about its atmosphere and surface features. For this reason, many planetary scientists strongly support sending a new mission to Uranus. Such a mission could place a spacecraft into orbit around the planet, allowing long-term observations of its atmosphere, rings, moons, and magnetic environment. Instruments aboard the spacecraft could probe the planet's interior structure and analyze the composition of its atmosphere. This type of mission would likely take more than a decade to reach Uranus, but the scientific discoveries it could provide would be invaluable. By studying Uranus in greater detail, scientists hope to learn not only about this mysterious planet, but also about the formation of ice giant planets in general. These worlds appear to be extremely common among the thousands of exoplanets discovered around other stars. Understanding Uranus may therefore help scientists interpret the many distant planetary systems that are now being observed across the galaxy. In this way, the strange sideways rotation of Uranus is more than just a curious feature of a distant planet. It is a clue to the violent and complex history of planetary formation, an ancient event frozen in time that continues to shape the behavior of one of the solar system's most mysterious worlds. As scientists continued studying Uranus after the Voyager 2 flyby, they realized that the planet might be far more important to understanding planetary systems than previously thought. For a long time, Uranus was often overshadowed by more dramatic worlds like Jupiter, with its giant storms, or Saturn with its spectacular rings. But as research into planets beyond our solar system began to accelerate, Uranus started to gain new scientific significance. Astronomers have now discovered thousands of planets orbiting other stars. Many of these worlds do not resemble the rocky planets of the inner solar system, nor do they match the massive gas giants like Jupiter. Instead, a large number fall into a category that scientists often describe as ice giant-type planets, similar in size and composition to Uranus and Neptune. These discoveries suggest that planets like Uranus may actually be among the most common types of planets in the universe. This realization has transformed the way scientists think about Uranus. Rather than being an obscure outer planet, it may represent a key example of a planetary class that dominates the galaxy. Yet despite its importance, Uranus remains one of the least explored planets we know. Only a single spacecraft has ever visited the planet. The Voyager 2 mission provided valuable data, but the spacecraft passed Uranus quickly. gathering observations for only a short period before continuing toward Neptune. Because of this limited encounter, many major questions about Uranus remain unanswered. Scientists still do not fully understand the planet's interior structure. The composition and layering of materials deep inside Uranus are largely unknown. Models suggest that beneath the atmosphere lies a deep mantle composed of water, ammonia, and methane in exotic fluid states created by immense pressure and temperature. But exactly how these materials behave inside the planet is still uncertain. Understanding the interior of Uranus is essential because it may explain several of the planet's most unusual features. One of the biggest mysteries involves the planet's lack of internal heat. Most giant planets emit more energy than they receive from the sun. This excess heat comes from the gradual release of energy stored during the planet's formation. For example, Neptune radiates roughly twice as much energy as it receives from sunlight. Uranus, however, is very different. The planet emits almost no extra heat. In fact, its atmosphere is the coldest of any planet in the solar system. Some scientists believe this could be related to the same event that caused Uranus to tilt on its side. If a massive collision occurred early in the planet's history, it might have disrupted the interior layers of Uranus in a way that prevents heat from moving efficiently toward the surface. Instead of rising through convection, the heat may remain trapped deep inside the planet. Another possibility is that Uranus simply formed differently from Neptune, leading to variations in internal structure that affect how heat flows through the planet. Future missions to Uranus could help answer these questions by measuring the planet's gravitational field and internal density structure. Another important area of study involves the atmosphere of Uranus. Although the planet appears calm compared with other gas giants, detailed observations have revealed that Uranus does experience storms and cloud activity. Bright clouds occasionally appear in the atmosphere, sometimes forming massive storm systems thousands of kilometers across. These clouds are thought to consist of methane ice crystals that condense in the cold upper atmosphere. Wind speeds in the atmosphere can exceed 900 kilometers per hour, moving these clouds rapidly across the planet. Scientists suspect that the extreme seasonal changes on Uranus may influence these atmospheric patterns. Because the planet's axis is tilted by nearly 98 degrees, sunlight shifts dramatically across the planet during its 84-year orbit around the Sun. Each hemisphere experiences decades of continuous daylight, followed by decades of darkness. This unusual pattern of heating may drive long-term changes in atmospheric circulation. Astronomers observed increased storm activity when Uranus approached its equinox in 2007, when sunlight was distributed more evenly across the planet's hemispheres. These observations suggest that the atmosphere of Uranus may undergo dramatic changes over timescales of decades. Another fascinating feature of Uranus is its magnetic field. Unlike Earth's magnetic field, which is generated by a molten iron core and aligned roughly with the planet's rotation, Uranus's magnetic field behaves in a much more complex way. The magnetic axis is tilted about 59 degrees relative to the planet's rotation axis and is significantly offset from the planet's center. As Uranus rotates, this unusual geometry causes the magnetosphere, the region of space influenced by the planet's magnetic field, to wobble in a complicated pattern. This creates dynamic interactions with the solar wind, producing unusual auroras and radiation environments around the planet. Scientists believe the magnetic field of Uranus may be generated in a layer of electrically conducting fluids composed of water, ammonia, and methane deep inside the planet. Studying this magnetic field could provide valuable information about the internal structure of Uranus and the behavior of these exotic materials under extreme conditions. The moons of Uranus also offer important clues about the planet's history. The 5 largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, each have distinct geological characteristics. Some appear heavily cratered and ancient, while others show signs of resurfacing or tectonic activity. Miranda, in particular, displays one of the most bizarre landscapes in the solar system, with enormous cliffs and strange patchwork terrain that may have formed through complex geological processes. These moons orbit in the same tilted plane as Uranus's equator, reinforcing the idea that the entire system formed after the planet acquired its sideways orientation. Studying the moons may therefore help scientists reconstruct the sequence of events that shaped the Uranian system billions of years ago. Because Uranus is so distant, almost 3 billion kilometers from the Sun, studying it from Earth is challenging. Even with powerful telescopes like the Hubble Space Telescope, only limited details of the planet's atmosphere and moons can be observed. For this reason, many planetary scientists strongly advocate sending a dedicated mission to Uranus. Such a mission could place a spacecraft into orbit around the planet, allowing long-term observations of its atmosphere, rings, magnetic field, and moons. Instruments aboard the spacecraft could measure the composition of the atmosphere, map the structure of the magnetic field, and study the surfaces of the moons in unprecedented detail. A probe could even descend into the atmosphere to directly measure its chemical composition and temperature structure. These types of measurements would greatly improve our understanding of how Uranus formed and why it rotates on its side. More importantly, they would help scientists understand ice giant planets as a whole. Since many exoplanets appear to be similar in size and composition to Uranus and Neptune, studying these planets in our own solar system provides an essential foundation for interpreting distant planetary systems. In many ways, Uranus may represent the missing piece in our understanding of planetary formation. It is a world shaped by ancient collisions, extreme seasons, unusual magnetic forces, and mysterious internal processes. And, although it appears quiet and distant when viewed from Earth, Uranus continues to hold secrets that could transform our understanding of how planets form and evolve throughout the universe. In the end, the strange sideways rotation of Uranus is more than just a curious detail about a distant world. It is a window into the violent and chaotic past of our solar system, a time when planets were still forming, migrating, and sometimes colliding with one another. Billions of years ago, the solar system looked very different from the orderly structure we see today. Instead of stable planetary orbits and quiet gravitational balance, the young system was filled with countless large bodies moving through space. Some of these objects were the building blocks of planets, while others were planetary embryos that had grown large enough to influence the motion of nearby worlds. In this turbulent environment, massive collisions were not rare events. Instead, they were a natural part of planetary formation. One of these collisions may have changed the fate of Uranus forever. At some point early in the planet's history, a large object, possibly a planetary embryo several times the mass of Earth's moon, may have struck Uranus at a glancing angle. Rather than destroying the planet, this impact could have transferred enormous angular momentum, pushing the planet onto its side. The result was a world with a tilt of about 98 degrees, unlike any other major planet in the solar system. Today, Uranus continues to spin sideways as it travels along its orbit around the Sun. This unusual orientation has shaped nearly every aspect of the planet's environment. Because the planet rotates on its side, sunlight reaches different parts of Uranus in extreme and unusual ways. Each hemisphere experiences decades of continuous daylight, followed by decades of darkness. These long seasons influence atmospheric circulation, cloud formation, and temperature distribution across the planet. The sideways orientation also affects the planet's rings and moons. All of the rings and major moons orbit in the same tilted plane as the planet's equator. This suggests that the moon system likely formed after Uranus acquired its extreme tilt. Debris created during the ancient collision may have gathered together over time to form the moons we see today. Even the planet's magnetic field appears to reflect the unusual internal structure created by this event. Unlike the magnetic fields of most planets, Uranus's magnetic field is tilted dramatically and offset from the center of the planet. This creates a magnetosphere that behaves in strange and complex ways as the planet rotates. Auroras form in unexpected locations, and charged particles from the solar wind interact with the magnetic field in patterns unlike those seen around other planets. The interior of Uranus may also hold clues to the planet's violent past. Scientists have long been puzzled by the fact that Uranus emits very little internal heat. Most giant planets radiate more energy than they receive from the Sun, but Uranus appears unusually cold. One explanation is that the ancient collision that tilted the planet also disrupted its internal structure. If layers of material inside Uranus became separated in a way that prevents mixing, heat from the planet's core may remain trapped deep inside. Without efficient convection to transport that heat outward, the planet's atmosphere would appear colder than expected. This possibility shows how a single event billions of years ago may still influence the behavior of the planet today. Yet despite everything scientists have learned, many mysteries about Uranus remain unresolved. Only one spacecraft has ever visited the planet: Voyager 2. When Voyager 2 flew past Uranus in 1986, it provided humanity's first close-up images of the planet, its rings, and its moons. However, the spacecraft's encounter lasted only a short time. After gathering data during the flyby, Voyager 2 continued its journey toward Neptune and eventually into interstellar space. Because of this brief encounter, our knowledge of Uranus is still surprisingly limited. Modern telescopes, including the Hubble Space Telescope, have allowed astronomers to observe storms in the planet's atmosphere and monitor changes in its weather patterns. but telescopes cannot reveal the deeper secrets hidden beneath the planet's clouds. For this reason, many planetary scientists consider Uranus one of the most important targets for future exploration. A spacecraft placed into orbit around Uranus could observe the planet for many years, studying how its atmosphere evolves over time. Instruments could measure the composition of the atmosphere, analyze the structure of the magnetic field, and map the surfaces of the moons in far greater detail than ever before. A probe could even descend into the atmosphere to measure temperature, pressure, and chemical composition directly. These measurements would help scientists answer long-standing questions about the formation of Uranus and the origin of its extreme tilt. But the importance of studying Uranus extends far beyond our own solar system. In recent decades, astronomers have discovered thousands of planets orbiting distant stars. Many of these exoplanets appear to be similar in size to Uranus and Neptune. These worlds, often called ice giants, may be among the most common types of planets in the galaxy. By studying Uranus in detail, scientists can learn how these planets form, how their atmospheres behave, and how their internal structures evolve. In this sense, Uranus serves as a natural laboratory for understanding an entire class of planets that exist throughout the universe. The sideways rotation of Uranus is therefore more than just an unusual planetary feature. It is a record of a dramatic moment in the early history of the solar system, a collision powerful enough to tilt a giant planet and reshape its future. Even after billions of years, Uranus still carries the imprint of that ancient event, as it continues its slow 84-year journey around the Sun, spinning quietly on its side in the dark outer reaches of the solar system. Uranus reminds us that planets are not static worlds. They are shaped by powerful forces, violent collisions, and the long evolution of cosmic history. And somewhere within that distant blue planet, hidden beneath layers of cloud and ice, the story of that ancient collision may still be waiting to be fully discovered.